Oh, right. So you missed lesson 6.1.2 called Kool Solutions. It first talks a little bit about how when you have a dehydrated patient, they need medical attention and they're often given an IV. And in the IV fluid, there are lots of different things that, depending on the patient's condition, that they may need, like salts and various sugars like dextrose. So they don't use just plain water in an IV, they use solutions. So we talked a little bit about why it's important for health professionals and scientists to have accurate concentrations, and mostly the class came up with ideas surrounding the fact that our bodies can only take so much of different ions, and we have a certain biochemistry that we need. So if a concentration is too high or too low, then that's not going to be good for our body. We also talked about in the second question here, if you have 100 grams of substance A that you add to 1 liter of solution, and you have 100 grams of substance B added to a different 1 liter of solution, is it possible for those two substances to have a different concentration? And the answer is yes, because substance A may have a higher molar mass than substance B. If you have 100 grams and you divide it by a bigger molar mass, that's going to result in a smaller number of moles. Since concentration is moles divided by liters, that means in my situation here, solution A would actually have a lower molarity or concentration. So in class what we did was we made 3 different solutions of Kool-Aid. Sorry you missed getting to drink some Kool-Aid. And to the first cup we added 2 grams of the sugar/Kool-Aid flavor substance, and what we did was calculate how many moles is that. Well, 2 grams of sucrose, that's C12H22O11, and I gave this out just to make the lab a little bit easier. The molar mass is 342.3. So 1 mole of sucrose weighs 342.3 grams. So 2 times 1 divided by the 342.3, we were adding 0.0058 moles of sucrose to cup number 1. Then, each cup had a line on it, and so we would add the sugar to the bottom, and then we would fill to the line. And the lines were measured out so that that was at the 0.24 liters mark, which is also 1 cup. And so for molarity, moles divided by liters, if we take our 0.0058 and divide by the 0.24, we get a molarity of 0.024. So 0.024. The appearance of this was very light pink or light blue, depending on the Kool-Aid solution you were drinking, and the taste was gross, very watery, at least to me. So in cup number 2, we added 12 grams of sucrose, the C12H22O11. So same molar mass, 1 mole sucrose. So we figured out in cup number 2, we were actually adding 0.035 moles of sugar. Again, divide by the number of liters to get the molarity. This one came out to be 0.15 moles per liter. And the appearance was more of a red color with the red Kool-Aid, and it tasted really good. If you like Kool-Aid. And for cup number 3, we added 24 grams of the sucrose to the cup, and filled to the line with water. And so this is actually double the amount of moles from that second cup. So it makes sense that this comes out to be 0.07 moles, twice as many as before. 0.07 divided by the 0.24 liters, and we found out that we had a 0.29 molar solution, so about 0.3. So I'm going to round mine up to 0.3. It was a little bit of a darker red here, and it tasted very sugary. Some people liked it a little bit better, but most people, it was a little too much sugar for them. So then we talked about, yes, we could definitely taste the difference in the molarities, and if we were trying to sketch a particle representation, cup 2 would definitely have more solute in the same amount of solution versus cup 3. I'm just gonna like shade it in, even more solute for the same amount of solution. Okay, then we did a slightly different scenario. What if we wanted to make 0.24 liters of a 0.5 molar Kool-Aid solution? So this is a lot more concentrated. The highest we made before was 0.3. So how would we go about doing this? Well, first we need to figure out how many moles are we going to need for this solution. We're trying to make 0.24 liters of a 0.5 moles per liter solution. So we need 0.5 moles for every 1 liter. So how many moles would we need for 0.24 liters? So when we multiply that, it comes out to be 0.12 moles of C12H22O11 that you would need. And so we got to multiply by the molar mass in order to figure out how many grams that is. So now we multiply by 342.3, and this comes out to be 41.1 grams. So then I'm supposed to describe the technique I would use. So I would add 41.1 grams of sugar to the cup and fill to the line with water. Then I would have a 0.5 molar solution. Makes sense too if you think about it, because 24 grams made a 0.3 molar solution, so it wouldn't be double 48 if you're going from the 0.3 molar to the 0.5 molar, but almost double. So rather than using a plastic cup, actual chemists use something called a volumetric flask to get an accurate concentration. So for example, if I wanted to make a 1 molar solution of sugar, I would add 1 mole of sugar, 342.3 grams, to this flask, and then I would fill to this line with water and dissolve it. Then I would have exactly a 1 mole for 1 liter solution. So this question says, what if I want to make a 0.05 moles per liter solution, and I want to make 1 liter of it? So I want 0.05 moles of my sucrose. How am I going to do this? Well, again, I know 1 mole of the sucrose is equal to 342.3 grams. So I'm going to need to multiply to figure out that I need 17.1 grams. And so I would put 17.1 grams of sucrose in the flask and fill to water line. I guess I should say fill with water. Fill to line with water, mixing along the way. what I've done there is I've added exactly that 0.05 moles of sucrose and made a 1 liter solution. So I've got a 0.05 molar solution. That's not the only way to make a solution though. So cup number 3 was way too sugary, so we called that our stock solution. That's the name that chemists use for a concentrated solution that they're going to use. Basically, they dilute it to a lower concentration. So we knew that cup number 3 was 0.07 moles in a 0.24 liter solution, and that molarity is 0.3. So how could we use that solution but basically cut that concentration in half and make it so that it was 0.15 moles per liter? Well, what we did was we took a cup with a line and we added a half a cup of the really diluted stuff from cup number 3, and then we filled to the line with just water and then mixed it up. So basically that number of moles does not change, but now it has more volume to spread out, and so it's half as diluted. So putting this with a calculation, we were adding 0.12 liters of that 0.3 moles per liter solution, which is the same as saying we added 0.036 moles of sugar to that new cup. But now, because there's more water in it, the total volume is 0.24 liters. Now the concentration is only 0.15 molar instead of the 0.3. So there's an equation to do this without thinking. I mean, who doesn't want to not think? Just kidding. But it's helpful when you're not just doing like a 50% dilution. It's called M1 times V1 equals M2 times V2. Well, I should say it's called the dilution formula. So you usually plug in the stock solution's molarity for M1. And V1 is what you're solving for a lot of times. So you're figuring out how much of that concentrated stuff should you add to an empty volumetric flask before you fill to the line with water. M2 is what you want, the molarity of your new solution. And V2 is how much of your new solution you want. So if we were to start that same Kool-Aid question over, we would say 0.3 molar stock solution times a mystery amount that we don't know equals, we want 0.15 molar and we want 1 cup of it, 0.24 liters. So in order to solve for V1, I divide both sides by 0.3 and I get a volume of 0.12 liters. So to finish this off, this is exactly what we did. We took 0.12 liters of the stock solution. I guess I should draw my cup a little bit better. Here's my cup with my line. We filled it halfway with the really concentrated Kool-Aid, and then we filled to the line with water and mixed it up to spread out those particles. So just to test yourself with pictures, which set of pictures depicts what's happening at the molecular level during this part? Well, I count 8 little dots representing my solute molecules. And in picture A, or scenario A, it's still 8 dots, but they're more spread out. And in letter B, there's 8 dots, but then there's more dots. So we weren't adding more solute. We were just adding water so that the solute would spread out and become less concentrated. Let's do one more question. What if you want to make a 0.75 liters of a 3 molar solution, and your concentrated stuff is 12 molar stock solution. So that's going to be my M1. I don't know how much of it I need to work with in order to make my 3 molar solution, and I want to make 0.75 liters of it. So first thing I'm going to do is divide both sides to get V1 by itself. And V1 here comes out to be 0.19 liters. Well, what does that mean? I've got a 0.75 liter flask, and what I'm going to do is I'm going to put 0.19 liters of the 12 molar stock solution in here, and then fill to the line with water. When I do that, this is my water. Once this all mixes up, the whole thing is now going to have a more dilute concentration of 3 moles per liter. So the making sense questions, there's a couple of them here. What are 2 different ways in general you can make a sugar solution? You can add solute to a flask and add water, or you can dilute a more concentrated solution. I guess I could have been more specific. It did say sugar. So I would add sugar to a flask and add water, or I would dilute a more concentrated sugar solution so that it would be 0.01 molar. When you dilute a solution, you add water to a concentrated solution and the concentration decreases. But the volume goes up because you're adding water. The number of moles stays the exact same. You're not changing that. You're just changing how much space they have in the solution. So if they can spread out more, it's more dilute. Sort of like the Kool-Aid. When you drink a watered down Kool-Aid, it doesn't taste as good because not as many sucrose molecules are flooding your taste buds as when you have Kool-Aid that's the correct concentration. And let's do the last 2 check-in questions here. We're going to use the dilution equation. It says I've got a stock solution. That's going to be my M1, 4 molar. And I want to make 100 milliliters of a 0.08 molar solution. I'm going to change my milliliters into liters just to keep consistency, but I don't have to do that. I could have left it in milliliters. I'm going to divide both sides by 4 to get V1 by itself. V1 comes out to be 0.002 liters. Times by 1,000, that's 2 milliliters. So I'm not done yet. Describe how I would make this solution. I would add 2 milliliters of the 4.0 molar solution to a 100 milliliter volumetric flask and fill to the line with water. So when I do that, I've got this really concentrated stuff, just a little bit of it here. Oops. It's my really concentrated stuff, 2 milliliters. And then the rest is just water. I'm not doing a very good job depicting this. So now my 2 milliliters of the really concentrated stuff spreads out in just the plain old water, and now the entire thing has a much lower concentration of 0.08 moles per liter instead of the 4 moles per liter. And the second one here, what if I measure out 200 milliliters of a 3 molar solution and then I add some water to it? What's the new concentration? Well, let's figure out how many moles of solute I've got. I've got 0.2 liters of a 3 moles per liter solution. That's 6 moles. Now my volume has changed. I had 200 mils, now I have another 400 milliliters of water. That's 600 milliliters, or 0.6 liters. Oh, this was 0.6, by the way. 0.6 moles divided by 0.6 liters is 1 molar. So hopefully that gives you a little bit of an idea of what you missed, or a little help going over that.